Okay, so let's think about what this thing does. Okay, shut up. It's my time to shine. Um, so let's think about what this thing does as you press that down. So there's there's like a vertical force pushing up. Whatever this thing is crushing here is applying a vertical force. And then there's like this thing can slide straight up or down. Okay, so you can think of that as like what whatever direction it would want to go. You know, there's a normal force pushing it back. Another way you could think of it is like imagine like this pin right here. Okay, imagine that on like a pin and slot joint. All it can do is go straight up and down. Okay, so that's how I'm going to treat this, like a pin and slot joint with a vertical force acting that way. Yes.
So if the big one is like A, or the big one is 1, and the like bar is 2, and the weight thing is 3.
Yeah.
How do we find the the length of 2?
From B to
Yeah, you just have to do that trigonometry, I guess. Oh, like what's the height?
Yeah,
You're saying-
what's the length or anything?
Mhm.
Because it only tells us
Yeah.
the angle.
Right. Well,
That's what I struggle
you
with.
extend.
okay. Well, let's just start doing it and let's see. So I'm going to think of this thing like I'm going to think of it as there's a pin that slides in a vertical slot, and you also have a force R acting that way that's from whatever it's supposed to be exerting a force on. And then you have this, and you have your force F. And that force F is a parameter that drives this thing. That's not something that you're trying to calculate. Are you with me on this? What I'm trying to get at here? I'm going to call this body 1, this body 2. I didn't even put the weight in at all. The only thing that matters to us is what's happening at that pin. Okay. And so let's draw this stuff. And so that R okay. So I'm going to do a free body diagram of body 1. There's RA. Here's F12. And here's F. And there's no masses or anything. I'm going to put my about point here. And then rho, force, moment. I'll start with RA. Rho vector is 0. Force is RAX, RAY. Cross product is 0. Then we'll go to F12. That rho vector is I'll just keep it all in millimeters. So 200 times cosine and sine is 60. So that row vector is 100, 173.2. The force vector is F12x, F12y. Cross product is 100 F12y minus 173.2 F12x. And then the force F. So that is, so the way I'm going to think about it is like I'm going to add two vectors to get the row vector for C. I'm going to add the vector from A to B, and then I'm going to add the vector from B to C. Okay? And so we already have the vector from A to B. The vector from B to C is 400 times cosine and sine of 15. So 386.37, 103.53. Force vector is 0, negative F.
We
So-
have to add that to the, because
Oh, I didn't add it. You're right.
that would be like 486 and then 276.
Yeah, so clear, add. Yeah, so 486.37 and 276.73. And then the cross product is negative 486.37 F. And so the first three equations are a x plus f12x is equal to 0. The second equation says ray plus f12y is equal to f. Remember that f is not a variable, so I'm going to put that over like it's a constant. And then the third equation says negative 173.2 f12x plus 100 f12y is equal to 486.37 f. Too many variables to solve anything yet. And now we'll go to body 2. And so, well, here is the thing about and I haven't talked about this yet, but this is a two-force body. And you could get the same answer by just assuming that was any length you want. But here's the reason that this could be any length and these answers are going to be the same. A two-force body is something where the only loads acting are force vectors at two different locations. In that case, static equilibrium requires the forces to be first equal and opposite, and second, directed along the line between the two locations. So let me just point out intuitively why this is the case. So think of a two-force body. Well, instead of doing it like that, let's first think about, so what if these two forces, one was that way and one was this way, okay? Is there any way that that thing could be in static equilibrium if those were the only two forces acting? No, it would spin, and depending on the magnitudes of those things, it might also be accelerating, okay? So in order for it not to accelerate, these two forces would have to be equal and opposite. Okay. So now the center of mass is not accelerating, but you can clearly see that that thing would spin. Okay. And so there's only two possible ways that this thing wouldn't accelerate and wouldn't spin. One is that the forces are exactly opposite each other along the line. Going away from each other along the line of the connection. And the other way is that they're just going towards each other along that same line. Those are the only two possibilities. Okay. And so if these two forces are, so if the forces on body 2 are going straight towards each other or straight away from each other, they're not producing any moment on that thing. And so because of that, it doesn't matter how long this beam is. You could make it 50 miles long, or you could make it an inch long. The moments are going to be zero anyways. The only reason we care about row vectors is for moments. Okay. So, yes?
Is this only if there are like pinjoints on either end, like there's no connection that's causing a moment?
Yes, that's right. So this only works if those two locations have force vectors acting on them. If there's anything else, if there's couples, it doesn't work. Yeah. So, okay, let's just give it a length. So I'm going to say, here's my coordinate system. And that angle is, so it's 20 from the vertical, which means this angle is 70 degrees. And so I'm going to, let's say the length is 200 millimeters. Okay, so let's draw the free body diagram. At the pin, we have the force on 2 by 1. That's negative F12. Then at the lower pin, we have a force vector due to the pin and slot joint. And the rule is perpendicular to the slot. So it's this way. I'll call that R. No, I'll call that R E. Okay. And then we have this upward force that I'll call N. That's the force it's applying to the nut or whatever it's crushing, you know? Yep.
So for this one, like on the answer key, like you made it a third, like kind of free body. That was
Oh,
like
okay.
infinitely like thin and infinitely short. But
Yeah.
we can also just model it as the force is just being on there.
Yeah, if you can just figure out what the behavior is, you know, like that, I mean, that pin isn't going anywhere. I also could have just said that that was a pin joint with the ground since it's not going anywhere, you know? So I just kind of did it the way that I thought of it this time, but those are all going to give you equivalent answers. Okay. And so notice that this is a two force body. I have these two things broken up into two different forces, but any forces that act at the same point, the total force vector of that point is just the sum of them. So this is just a force vector up at the top and a force vector down at the bottom. That's a two force body. Okay.
We guys just one force and like, you know, RD of X, Y.
Yeah, you could do that. That would give you the same answer. Okay, so rho, force, moment. I guess I'll put my about point here. So negative F12 has a rho vector of 0, force vector of negative F12x, negative F12y, cross product of 0. And then RE. So I just arbitrarily gave this thing a length of 200. Which was kind of the same length as that other piece. And so this rho vector is 200 times the cosine and sine of negative 70. So this rho vector is 68.4 and negative 187.94. The force vector is RE0. So the cross product is 187.94 RE. And then N, same rho vector. Zero N is the force. Cross product is 68.40 N. And so equation 4 says negative F12x plus RE is equal to 0. equation 5 says negative f12y plus n is equal to 0. And equation 6 says 187.94 RE plus 68.40 N is equal to 0. Okay, and then you can solve that. Probably everybody's good at this point. You could have made that. So, like, what are some reasonable assumptions you could make? Like, maybe you looked at it and thought, like, okay, maybe that pin is the height of A or whatever. You could use that length constraint. But really, the key to doing this problem without, and I think actually in my solution, there's a chance that I did that, just assume that that was the same height as A. But really the length of it doesn't matter. And the reason the length doesn't matter is that those forces just have to be equal and opposite along the same line. And so those forces aren't going to produce any moment on that thing. And the only reason that the length matters is because of whatever moment would be produced.
So in this one, you only have 4 variables at the end?
Let's see. I have RA, X and Y, F12, X and Y, and then 2, so 6 and 6.
Yeah. And then your answer is going to be in terms of P?
Are in terms of, oh, is that a P? Let me look closer. Yeah, P. I have it as F. Right.
So when you find your matrix, you just put 1?
So the only, so let's see. P. Okay. So, yes, you can do it as, so as long as every one of these expressions on the right side is multiplied by P, which it is in this case, you know, there's not a single constant here that isn't multiplied by P. Here and then here, they're all 0. So like you could think of this as, well, and as long as that's the case, that every constant on the constant side is multiplied by P, then yes, you can just treat P like 1, get those answers, and then your real answers are that times P. And I don't think I could explain why without going into like linear algebra and stuff. But that's a rule that's always true, you know. Any other questions about that one? Yeah. Okay, and now number 5. Yeah, I'll just go through the free body diagrams on those, sort of the thinking of all that. Ugh. My computer's acting screwy today. Okay. So I'll number these. 1 is this whole horizontal thing. 2, 3, 4, 5. So free body diagram of member 1. Okay, so what's going to matter here is with all these different bodies connecting at joints, you have to think at each joint, what's the lowest numbered member? And then based on that, you have to think about what's touching what. So, well, this one isn't too hard. The connection between 1 and 2, because there's only 2 bodies touching. But the pin is part of member 1. Here, the pin is part of member 2, okay? Which means 3 and 4 are each touching 2, but 3 and 4 aren't touching each other, okay? That's the key thing. So like when I do a free body diagram of member 2, up here, there's going to be an F2-3 and an F2-4, okay? But when I do a free body diagram of 3, there's only going to be a negative F2-3. There's not going to be an F3-4. Okay. And like, okay, now what about at this one? The lowest numbered member at this one is member 1. So member 1 is going to be in contact with 3 and 5. But 3 and 5 are not going to be in contact with each other. Each one of them is only going to be touching member 1, the pin. Okay? Any questions about what I'm talking about? Okay, so, and if you're ever confused about it, you can always draw the side view of the joint, shade out all the parts that are part of the lowest numbered member, and then you can actually see what's touching what. Okay, so free body diagram for 1. There's a fixed joint at the right. So I'll call that RA. Let me label these joints. So that's A, B, C, D, E. So there's RA. And then here, there's a force on 1/2. And then over here, if I did a side view of joint D, let's say I'm looking at it from the left side of this picture, there would be member 1 like that, and there would be member 3 like that, and member 5 like that, and they would all be connected by a pin. And the pin is part of member 1, so this is all member 1. So from this, you can see that acting on member 1 is there's a F13 and there's also an F15. And then I'll go to body 2. Down here, there's only a force on 2 by 1, so that's negative F12. Up here, 2 is the lowest numbered member, so we have a F23 and an F24. Free body diagram of member 3. Okay, so up at the upper right, the lowest numbered member is member 2. Okay, so let's do a side view of C. So we would have like member 2, member 3, and member 4. They're all connected by pins, by a single pin. That pin is part of member 2. And so that is the joint up in the upper right. So you can see that touching member 3 is only member 2, only that pin. Number 4 isn't touching it. So here we only have negative F23. At D, the lowest numbered member is 1. And so on 3, you can see 3 and 5 aren't touching each other. All you have here is negative F13. Any questions about that one?
I have a question
Yeah.
on how you would do the row vector for that one.
The row vector?
If you put your row point at the, like on free body diagram 3, like at negative F13, then for the row vector to negative F23, would you just use the angle of 20?
Yeah, you know that. So what does it give you? It gives you that this angle is 20 degrees. So you know that this angle is 20 degrees.
So just cosine
From geometry.
and sine of 20.
What?
So just cosine.
Yeah, cosine and sine of 20, that's right. Oh my God, my computer. What is going on? Okay. And now we'll go to member 4. So that's the top one. That one has the distributed load acting on it. At pin C, there's only a force on 4/2. So that's negative F24 because we've already used, we've already used 2,4. And then over at E, it's in contact with 5. So this is F4/5. And then member 5, so up at the upper left, there's only contact with member 4. So this is negative F4/5. And then at D, it's only in contact with member 1, so negative F15. Okay, we haven't counted the variables. Anyone have a guess how many variables there are? Yes, very good. Yes. So we could count the variables and hopefully that's how it'll come out. But we know it's easy to know how many equations there are. So if this is solvable, there need to be 15 variables because each one of those rigid bodies gives you 3 equations. Okay. Oh, and I messed up one thing on my free body diagram on member 1. Actually, if we counted the variables right now, there'd be 14 variables because I didn't, this is a fixed joint over here at A. And so I didn't put the couple on here.
Can you go to the last free body diagram?
Mm-hmm. And on exams, when like structures that I put on exams, obviously like I can't put a problem like this on an exam, on a 50-minute exam. It takes way too long. But one thing that I often do is I'll just have you do nothing but the free body diagrams of a complicated thing like this, just so I know that you understand how the joints work. Okay. Yeah. Yeah. I mean, not necessarily, but basically my 2 options are asking for free body diagrams of a complicated thing or asking you to solve a simple thing, you know? Yeah. Any other questions about that one? Okay, so I'll just give you 2 or 3 more to work on. And then I brought these whiteboard markers because one of the next things I want to do, sometime when there aren't a lot of homework questions or whatever, is I want to write a problem up on the board and I want you to get in groups and we'll just go through it step by step, just keep getting practice with that stuff all together. And then if you get something wrong, then everyone in your group gets to spank you. It's really good. Okay, bye.